Hello geometry students, I'm super happy to be working with you again. Hopefully you've had a good day and you're settled down with a piece of paper and a pencil and ready to write your notes. Today's lesson is 3.4, Proofs with Perpendicular Lines. I've already written that on the board, and I've been lazy here. Instead of writing the word perpendicular, I just have the symbol for it, which is the upside down capital T. So make sure that you go ahead and put that at the top of your notes. We're going to talk about some theorems related to perpendicular lines, and we can use these theorems when we're trying to prove things about lines. Now, the first fact that I want you guys to know is what we mean by the word distance in math. If we're talking about the distance from a point to a line, we always mean the distance along the line that is perpendicular to that one. So the story I like to tell about this is like with an airplane, and I have to tell you I am horrible at drawing airplanes. But if you can imagine that this point kind of represents an airplane. Everyone always tells me it looks like a goldfish, and I agree it does. But if this represents an airplane there, or something else, maybe a fish, if you're flying on an airplane and the pilot says to you, "Good afternoon, ladies and gentlemen, we are currently flying at an altitude of 20,000 feet, he doesn't mean, from here to here, right? He means straight up and down. So when we're talking about distance or altitude, we always mean straight up and down along a perpendicular line there. So it's just really important you know that when someone says distance in math, they mean the shortest possible distance. And so we can use that fact to solve a variety of problems. So let me give you an example like one that comes up on the homework. We'll call this example 1. In this example, we have 2 points in the coordinate plane, and point A is at -2, 3. So I'm going to go 2 to the left and 3 up. I'm going to put -2, 3 and put an XY underneath there. And point B is at 2, -1. So I'm going to put a 2, -1 under that. Then we're just going to draw a line here through B and another one through A going to B. All right, don't worry if you don't have all of this picture there. The main thing is to have those 2 points. The direction on this example might say, find the distance from point A to line M, given that AB is perpendicular to line M. What they're basically telling you is that this is the shortest distance, and they want you to use the distance formula to find the length between A and B. So this formula, unfortunately, is never going away. I know we learned it in chapter 1, but it's going to come up in every chapter since then. And as you probably recall, it's the square root of y2 minus y1 squared plus x2 minus x1 squared. Now I'm going to go a little bit on the fast side for this because it's something we've already covered. But if this is something you're still becoming comfortable with, please feel free to pause the video if you need to. So we would have -1 minus 3 in our first parentheses squared, and then 2 minus -2 in the second parentheses squared. Keeping in mind that 2 negatives in a row turn positive, we would have the square root of -4 squared plus +4 squared, or the square root of 16 plus 16, or the square root of 32. Now we could simplify that by pulling out pairs, but since we're talking about a distance that we might want to measure with, say, a ruler, if it's in inches or whatever, we're going to say this is about 5.7. So 5.7 units. All right, now we're going to learn the names of some theorems and what they mean. There's 4 of them. The first one is called the linear pair perpendicular theorem. And again, we're having to write the word perpendicular so much in these notes. It can be really helpful to you to use a capital upside down T for the word perpendicular because it will take a little bit less time. So I'm going to read you what it means, but then I'm just going to draw you a picture because I think it will be easier in your notes to have the picture. This theorem says if two lines intersect to form a linear pair of congruent angles, then the lines are parallel. So that's really a mouthful. I don't want you to worry about writing it down. What I'm going to have you do instead is just draw this picture here. So we have two lines, lines L and M, and they intersect to form a linear pair. What happens is that if angle 1 is congruent to angle 2, then L is perpendicular to M. Now, why would that be? If they form a linear pair, we know they have to add up to 180, right? But if they're the same angle, they would both have to be 90. So if these are two 90-degree angles, then it would make sense, yes, the lines are perpendicular. So that one, once you see the picture, I think that one does make sense. All right, the next one is called the perpendicular transversal theorem. And this one says, if a transversal is perpendicular to one of two parallel lines, then it is perpendicular to the other one. So let's draw a picture. We know that we need two parallel lines, so let's go ahead and draw that. Let's call these lines L and M. And let's show the transversal perpendicular to one of them. How about line L? And I think I'll call this line P. So let's just say then, if L is parallel to M, and let's be sure to mark that on here. So if those two lines are parallel, and L is perpendicular to P, so here L is perpendicular to P, then we also know that P is perpendicular to M. Okay, so if a transversal, that's line P, is perpendicular to one of two parallel lines, that's called that L, then it is also going to be perpendicular to the other one. So P would be perpendicular to M. All right, there's two more, and then I think that maybe I'll do one more example, and then we'll talk about more of this when we actually do the homework. Okay, the next theorem is lines perpendicular to a transversal. That's our next theorem, lines perpendicular to a transversal. So I'm going to read it, but again, I primarily want you guys to do the picture because I think that that'll be easier to put in your notes. And actually, to give you a little bit more space, I'm going to put it over here. So I'll rewrite it just to make it more clear. This was lines perpendicular to a transversal. Okay, so here's the words, and again, you don't have to write the words, but in a plane, if two lines are perpendicular to the same line, then they are parallel to each other. So let's draw a picture of that. We have two lines, let's call them M and N. And again, feel free to pause here. If they're perpendicular to the same line, let's call that line P, then they're parallel to each other. So if M is perpendicular to P and N is perpendicular to P, then M is parallel to N. I'm so sorry about all this writing. I know it kind of sucks. We're doing the best we can. Okay, the last theorem is the transitive property of parallel lines. We'll do this theorem and then probably one, maybe two examples. All right, so let's draw three lines that look like they're parallel to each other. Let's call them P and Q and R. So if P is parallel to Q, P is parallel to Q, and I'll just make this be more of a R, and R is parallel. Q is parallel to R. Let's do that order, might make more sense. Then P is parallel to R. So let me read that again. If P is parallel to Q, so this line parallel to this one, and Q is parallel to R, then P is parallel to R. So those are the four theorems. Now, again, this is a lot of writing that we have to do. It's not easy to get it all down. Please pause as you need to make sure that you get all the theorems down. The other thing, of course, that you can always do is go online to the book, the Big Ideas book. There's instructions on my website on how to do that, and you can see the information written there. So let's go ahead and do one example here. We already did example 1, so we'll call this example 2. Determine which lines are parallel to each other. So I'm going to draw lines A and B here, and then lines C and D here. And then I'm going to put a right angle here and a right angle here. So I'd like you to kind of look through the theorems that we just talked about, see if one of the pictures might kind of match up with that one, and if so, what two lines do you think would have to be parallel? Well, one big clue we have here is that there's really no information about line A. So it really is centered around this part of our picture. So what we can say is that C is parallel to D. Now, do you know which theorem we would use to prove that of the four that we learned? What picture does that look the most similar to? The theorem that it's transversal to is lines perpendicular to a transversal theorem. And again, what that theorem tells us is that if two lines are perpendicular to the same line, so C and D are both perpendicular to B, then they must be parallel to each other. That was the lines perpendicular to a transversal theorem. So that's how we proved that one. Okay, let's go ahead and do one more example of 3 lines here. So I've got lines P, lines Q, and lines R here. And then we're going to have going this way, line M and N. This is example number 3, and it is your last example. Hallelujah for these notes. Okay, I'm going to draw a bunch of right angles here, 2 here, and 2 here. Now, this is kind of a nasty problem, but the reason I put this on here is it's basically identical to one of the homework problems. And sometimes, this is a hard one. Sometimes if you see something more than once, it can make it easier to process. So if you're watching the video and hearing me say it now, then when we do the homework and this same kind of problem is on the homework, it might make more sense then. So we actually know a few things here. We know that M is parallel to N, so I can write that down. Does anybody know why M and N would need to be parallel to each other? I'll highlight the part of the picture that would apply. M has to be parallel to N because they are perpendicular to the same transversal. If you look at this box right here and this box right here, M and N are both perpendicular to R, so they must be parallel to each other. So that would be the theorem that we just learned. Lines perpendicular to a transversal. So let's write that here. Lines perpendicular to transversal. Okay, there's another pair that we can say is parallel, and that would be lines P and Q. P and R. So P parallel to R. I'm going to change these back to black boxes here. And I want you to look at the diagram and see why would it be that P is parallel to R? Why would P be parallel to R? I'll show you the boxes that would be involved. It would be this one here and this box here. So P would be parallel to R for the same reason we just used, because they're both perpendicular to the same transversal. They're both perpendicular to N. So again, we would say lines perpendicular to transversal. You can put the word theorem after that, but you don't really need to. Okay, so we've got that. Let's do another one. Hopefully you're kind of seeing a pattern here. Q is parallel to R. Q is parallel to R. So let's look at the picture and see if we can figure out why is Q parallel to R. The box that you would want to look at, the boxes, would be these two right here in this case. It's again the same reason. Q and R are both perpendicular to M, so they must be parallel to each other. So same reason, lines perpendicular to transversal. Now, can anybody see, based on this pattern here, one more pair? I'm going to tell you what it is and see if you can figure out why. Why is it that P is parallel to Q? Why is P parallel to Q? Now, P and Q are not perpendicular to the same transversal, so it's not the reason that we just used. It's one of the other theorems, and this is the last part of our notes. And I'll give you a hint. It has to do with this information here. The reason is the transitive property of parallel lines. Now, while you guys are kind of mulling over that, let me explain it, and then I'm going to do one other thing for you. P is parallel to R. R is parallel to Q. So since they're both parallel essentially to the same line, they must be parallel to each other. So we would say the transitive property of parallel lines. Now, there is one other thing that comes up in the homework, and it's a construction. So I am going to include it on these notes just because I want you to be able to have everything that you need in one spot for this. So in these notes, or this part of the notes, we're going to be using a ruler and a compass and protractor. So we're going to use a compass and a straight edge to construct a line perpendicular to line M through point P. So what I want you to do at the very end of your notes is draw line M. And I super appreciate your patience. I know this has been a really tough one. And then I also want you to draw point P above it. And I'm going to read you the steps step by step. The first step is to place the tip of your compass at point P and draw an arc that intersects the line twice. So what you need to do is open up the compass enough. You don't want it to be too short because then it won't intersect the line at all. And you don't want it to be too big because then it won't even show up on your paper. But you want it to be big enough so that when you move your compass, you put your tip on P and you move your compass and it's going to intersect that line twice. And again, you can stop this video and rewind it as you need to. Then we're going to label the points of intersection A and B here. Then we want to put the tip of our compass at point A and draw an arc below the line. Now, keep your compass tightened when you're here. We're going to draw an arc down there. Keeping that same setting, put the tip at B and draw another arc. So we put our tip on A, we drew one arc, we made sure that the compass was tight, we moved the tip to B, and we drew another arc using that same setting. we're going to label the intersection of these two arcs Q. Then we're going to draw line PQ. And when we draw line PQ, it might not be perfect. This one's actually not too bad. But when we draw line PQ, it should be perpendicular to line M. So you guys have been amazing. This has been a tough notes. Thank you for hanging in there, and I'll see you in Zoom.